Now we want to talk about eigenvalues and eigenvectors. This is really one of the key concepts when it comes to data analysis and also machine learning, because many algorithms use these concepts. Eigenvalues and eigenvectors, if exist, are a particular simple way to describe linear operators, and we use it in principal component analysis, singular value decomposition, in spectral clustering. So there are many applications that really need eigenvalues and eigenvectors. Formally, they are not so complicated to define, and I think they also convey a lot of intuition about linear algebra, and hopefully I managed to convey some of this intuition now. Let us, as usual, start with a definition. So, we consider a linear operator T from V to V. And now we want to say when is a scalar number an eigenvalue of this linear operator. So a scalar lambda in F, again our field is typically R or C, the complex numbers, is called an eigenvalue if there exists a vector in the vector space, and important, it must not be the zero vector, such that T times the vector is lambda times the vector. So what does this mean? We have a vector, and if we apply the linear mapping to this vector, the output is just a scaled version of the linear vector, and the scaling factor is lambda, and this is the eigenvalue. So we might have a linear mapping that, for example, realizes a stretching along a particular dimension, and then in this direction the eigenvalue is, for example, 2, and the vector in which direction we just stretch is the eigenvector. So I write down that it's called the eigenvector. So a vector V with this property, so with the property that T times V is the same as lambda times V, is called an eigenvector. An eigenvector corresponding to eigenvalue lambda. This is a bit cumbersome. Typically we just call it the eigenvector if we know which eigenvalue we're currently talking about. It's called an eigenvector corresponding to eigenvalue lambda. And now we need to talk about an eigenspace, the set of all eigenvectors of lambda, of this eigenvalue lambda, is called the eigenspace. And so formally, if you want to write it down, the eigenspace corresponding to eigenvalue lambda of operator T, it is the kernel of the linear map T minus lambda, the identity. Observe, maybe I explain it in a minute what the intuition is. Maybe just do it now. So observe, if we have T times V is the same as lambda times V, this is the same as saying T times V minus lambda times V is 0. And now you can write this as T times V minus lambda, the identity V is 0. And you can also write this as T times, T minus lambda, the identity operator, times V is 0. This is the intuition why we often, when we talk about eigenvalues and eigenvectors, we always consider this operator T minus lambda, the identity, and this is where it comes from. Okay, let me maybe start with a couple of remarks. So I already said that an eigenvector realizes a stretching, and I maybe write it down, remarks. An eigenvalue eigenvector realizes I just write it down, stretching. I don't know whether this is the correct English term. What I mean is that we have a linear mapping, and in one direction it just stretches the corresponding vector by the factor of lambda. So because what happens is this linear mapping maps v to lambda times v, so it just stretches this vector. It is important to notice that many mappings might not even have any eigenvectors. So many mappings do not have eigenvectors. And the obvious first candidate is a rotation. If I have a rotation which simply takes an object and rotates it, then there is not a single vector whose image is just a stretched version, because all of them get rotated, so their direction changes. For an eigenvector, the direction must not change. For example, a rotation. Then the next remark is, if lambda is an eigenvalue, it always possesses many eigenvectors. So if lambda is an eigenvalue, it has many eigenvectors. And this is really important. And the obvious thing is, if you have an eigenvector, then A times the eigenvector is also an eigenvector. So, for example, if, say, V is an eigenvector of lambda, an eigenvector of, well, I just write an eigenvector of operator T with eigenvalue lambda, then also A times V for A and K is an eigenvector. Because, I mean, if you just observe T of A times V, this is the same as A times T of V by linearity. We already know that T of V is an eigenvector, so we know it's A times lambda times V. And I can reorder this. This is the same as lambda times A times V. So we see that also for this, so T of A times V is the same as lambda A times V. So again, we stretch the vector by a factor of lambda. So whenever we have an eigenvector, any scalar multiple of this vector is also being an eigenvector. In general, it can be that we have also eigenvectors that, like of the same eigenvalue, that point in different directions. So in a minute we are going to see if we have distinct eigenvectors, then like corresponding to distinct eigenvalues, then these are always linearly independent, but we can have dependent eigenvectors for the same eigenvalue. I write in a minute, or I don't write this down. So we are going to see eigenvectors corresponding to distinct eigenvalues are linearly independent. And maybe I might as well write down the intuition why this is the case. Intuition. Assume maybe that lambda 1 and lambda 2 two eigenvalues. And of course I want to assume that they are not the same, because I want to talk about distinct eigenvalues. So assume we have two eigenvalues which are not the same. Assume that V1, V2 are eigenvectors that correspond to these eigenvalues, and assume that they are not linearly independent, or eigenvectors that are not linearly independent. What does it mean? It means that we can write one as a linear combination of the other. So it means, let me just check my notation that I use the same constant. So I can write the vector v2 as c times the vector v1, where c is a scalar factor, right? But now observe what happens if I apply the linear operator. So now I can apply, I know that t times v1, because v1 is an eigenvector of eigenvalue lambda 1, is lambda 1 times t, times v1, sorry. And now I can also look at what happens to v2. Of course, I know it is lambda 2 times v2 because it's also an eigenvector, but now for this other eigenvalue. But now, because I have here this property, I would be able to also write, this is the same as lambda 2 times c times v1. Okay, so this is the one thing, but I could also write it in this way. I could start tv2 is t times, and now I replace c times v1 in this position. Maybe I make another blue line here. And this is c times tv1, and again I know that tv1 is c times lambda 1 v1. Sorry, it's hard to read. I write the lambda a bit nicer. Lambda 1 v1. But now we have a problem here, because how can I mark this now? In orange maybe. So now I have these two expressions. One says lambda 1 v1 c, and one says lambda 2 c1 c lambda v1. So this is the same expression. So this is obviously not the same expression, because lambda 1 is not the same as lambda 2. But we started with the same. But here we started with the same expression. We started with exactly the same term. So somehow this is impossible. So here we have a contradiction. So what this says is, and the contradiction is to the linear dependence, to this blue thing I have just on my slide. Okay, so what we see is, if we have eigenvectors that correspond to distinct eigenvalues, they are always linearly independent. But the other thing I want to remark is that eigenvectors for the same eigenvalue do not need to be linearly independent. So eigenvectors that correspond to the same eigenvalue do not need to be independent. And we have already seen the example earlier. If you have just a vector, then A times the vector is also an example, the simple example. If V is an eigenvector, I often abbreviate it now as Eig. And Eig can either mean eigenvalue or eigenvector, and in this case it means an eigenvector because V is a vector, so not a value. So if V is an eigenvector, this also implies that c times v is an eigenvector, and of course these are not linearly independent. It's the same vector just multiplied. But v and c times v are not linearly independent, obviously. So they do not need to be linearly independent, but they can be linearly independent. They can be linearly independent. I could just design a mapping that takes two vectors which are linearly independent and stretches them by a factor of 2, and then of course both have the same eigenvalue, but the vectors are linearly independent. And the most prominent example is the identity mapping, easy example. If I consider the mapping A, which is the identity mapping, then every vector is an eigenvector. Then every vector B is an eigenvector of eigenvalue 1. Because I have identity times the vector is 1 times the vector, so it's an eigenvalue 1, and this holds for every vector. So in particular, if we have independent vectors, it could also hold. Okay? So once things have the same eigenvalue, you can't make any statement. But we can make maybe a bit of a better statement. The eigenspace corresponding to an eigenvalue lambda of some operator t is always a linear subspace of the original vector space. So it could be, by subspace, it could also be the same, like the identicals, like the original space V, like in the identity operator example. But in general, it's a subspace. And this is easy. This is something that you might want to prove. You might want to prove that if you have. So you say, okay, what do you have to prove? First of all, it forms a subset because we just defined E of lambda t as being the set of elements for which are an eigenvector. And now you need to show that if you take linear combination of two such elements, they're in the same set again. So it really is. So the set is closed under taking linear combinations, and then there you go. This is really easy. Just try to write it down. This is just one line. Okay. So these are the first remarks I wanted to make. Let me just see. And we're going to manipulate eigenvectors and eigenvalues for the next couple of lectures, so maybe you get familiar with them, or hopefully you get familiar with them. So I urge you to get familiar with them, because you can't survive machine learning without knowing what an eigenvector is and also having an intuition of what an eigenvector is. I want to show you one more proposition, which is also pretty clear, but still it sort of helps sometimes. For a finite dimensional vector space, the following conditions are equivalent, or the following statements are equivalent. The first one, lambda is an eigenvalue of linear mapping T. Then the mapping T minus lambda identity is not injective. And this is easy to see if there is an eigenvalue. If lambda is an eigenvalue, then you have an eigenvector, and the eigenvector is exactly the one that lives in the kernel of this mapping, so it can't be injective. And then we know that for finite dimensional vector spaces, we know that if a linear mapping is not injective, it's also not surjective and not bijective. So these properties are all equivalent on finite dimensional spaces. This is not true on infinite spaces. But here I can write it down. T minus lambda identity is not surjective. And the other thing, it is not bijective. And as I said, the proof is pretty easy and clear because of the properties like injective, surjective, and bijective are equivalent on finite dimensional spaces. And like going from 1 to 2 or 2 to 1 is essentially just the definition of what is an eigenvector. So this is really easy to prove. I'm not going to write it down. I want to make one more proposition regarding eigenspaces. Proposition. Suppose V is finite dimensional and T is a linear operator on V, and assume that lambda 1 to lambda m are distinct eigenvalues of T. Then a sum of eigenspaces of the form you take the sum of E lambda 1t plus E lambda 2t and so on until you, plus E lambda mt. So this is already a direct sum. It's not just a sum, it is a direct sum. Is a direct sum. And in particular, if the dimensions, like in a direct sum, the dimensions always add. So the dimension of the first eigenspace lambda 1t plus the dimension of the second one and so on until plus the dimension of the last one, E lambda m comma t. This dimension is smaller or equal to the dimension of V. Okay? It can be strictly smaller because it might be that we don't have any eigenspace, like in the case of a rotation. It could be that we just have, it could also be exactly the dimension of V, as we have seen for the identity mapping, for example. Or it could be anything in between. So for example, if you consider, so there are many operators which have maybe one or two eigenvalues, but the eigenspaces don't. So for example, in one direction, in one coordinate direction they stretch, but in the other direction they perform a rotation. Then we would just have one coordinate, we would have one eigenspace, and this would have a dimension that is strictly smaller than the dimension of the original space, but it's larger than 0. So everything can happen. Okay. Now, what we are really interested in is when do operators have eigenvalues, and if yes, how do they look like, and so on. And this is going to keep us busy for a while. Now I want to present you a first proof that over the complex number, every linear operator has an eigenvalue, and at least one eigenvalue and eigenvector. And now this is one of, when we start talking about eigenvectors and eigenspaces, this is one of the few places in linear algebra where it really depends on whether we operate over the complex number or over the real numbers. Because over the real numbers, a rotation does not have an eigenvector. Over the complex space, a rotation does have an eigenvector. And we're going to see that. So maybe first of all, let us look at the following theorem. Every operator T that goes from V to, so we have a vector space V, the operator goes from V to V, on a finite dimensional complex vector space V has at least one eigenvalue. Here, two words are important: finite dimensional and complex. Both words are important because it does not necessarily hold for infinite dimensional vector spaces. You could have elements in the spectrum that are not eigenvectors, and for real vector spaces, as we have seen in the case of the rotation, there might not even exist an eigenvalue. Okay, and this is a theorem that I find so important that I want to present you one proof. And the proof is a bit funny. It is a bit of an unusual proof. At least if I would give you the exercise or the assignment, or if someone would give me the assignment, prove the theorem, this is not without any other background knowledge, this is not the proof you would immediately think about. So let's look at this. Let's look at the proof. So we say n is the dimension of V. Simply, we are in a finite dimensional space, so we know this dimension is a finite number. Now we choose a vector. Choose a vector v in V. It can be any vector, except it should not be the 0 vector. So you just pick a vector. And then we consider now a set of vectors, the set. Let me first write it down. We consider now the set consisting of V, Tv, so we apply the linear mapping once to V, T square V, until we end up with T to the power of n times V. So recall, T to the power of something means I apply the operator so many times as we have in the exponent. So now we consider this set. The set consists of n plus 1 vectors, and because we're in an n-dimensional space, this set has to be linearly dependent, because in a finite dimensional space of dimension n, there cannot be any set of size larger than n that is linearly dependent. Then the set blah 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 has to be linearly dependent. Again, it consists of n plus 1 vector. It consists of n plus 1 vectors in an n-dimensional space. Okay. Now, we know it's linear independent, so we can find coefficients that if we take a sum of these vectors, we end up with 0. So now we say we find coefficients a0, a1 until an, such that a0 times v plus a1 times tv plus and so on, an times t hoch nv is 0. Okay, and we can find these coefficients because we know it's linearly dependent. And now, and for now it's a bit strange, why do we consider these kind of operators and so on. And now comes sort of the trick. So there's, and we're going to see that a bit later, there are lots of connections between eigenvalues and polynomials. And now what we do is we now consider a polynomial that has exactly the same kind of coefficients, but is now a polynomial and not a sum of operators. So now consider a polynomial on C. So it's going to be, we are going to operate on the complex numbers with exactly these coefficients. So let me write it down. So we define the polynomial P of Z is defined as a0 plus a1 times Z plus and so on, plus until an times z to the power of n. Now this is a polynomial over the complex numbers, and this is, here comes now the key why we need to be on the complex numbers. On complex numbers we know that we can factorize a polynomial. It has a representation in terms of individual one-dimensional factors. So now over C we can factorize it. So it means that we can write the polynomial in forms of c times z minus lambda 1, z times z minus lambda 2, and so on, z minus lambda n. So this is a polynomial of degree n. You can always write it in terms of a product of linear factors of n such linear factors. And these lambdas are the zeros of the polynomial. Oh, hang on, I made a mistake, and it was not entirely sure what I said at this point. The number of factors at this point, it does not really necessarily need to be n. So n is the dimension of our space, and n is, maybe let me just denote it. So n is here the highest coefficient, and here this m not necessarily needs to be n, because it could be, for example, that this an here is 0. And then the polynomial would be a degree less, and then the m and n do not necessarily need to match. Maybe I write it, n and m can be different. Of course, m needs to be smaller or equal to n, but it could be strictly smaller. But this doesn't really matter, this is just a side remark, which I make because I had this, I made this mistake in writing n instead of m. And now, what do we now do? We have the factorization of the polynomial, and now we use this also as a representation for our linear operator. And this is sort of, okay, let's simply do it. I write it down. Hence, what do we have? We know 0 is, I mean, by definition of our coefficients, we know that, sorry, this is wrong. A0 times v, a1 t times v, and so on until an t to the power of nv. We know this is 0. This is by the definition of these coefficients r. And now let me just make sure I don't lose where I want to go. Now what can we do? First of all, we take the v to the, so maybe I simply write it down and then I say it. So it is a0 plus a1 times t plus and so on plus an t to the power of n times v. So this is essentially by linear. So we can consider by linearity. We take v. So sort of we group the operators first and then apply v. This is a consequence of being linear. So this is now, and now let's see, this guy here, this is now a linear operator. And I can write this linear operator now in form of the product. So I can write this as c times t minus lambda 1 identity, t minus lambda 2 identity, and so on, t minus lambda m identity. Okay? This is now just another way of writing this linear operator. And observe, like formally, if you want, all I do is, I mean, maybe one needs to think about for 5 minutes why you can actually do this operation. Like if you have the factorization of the polynomial, why do you also get a factorization of these linear operators? But it is true. Okay, now maybe I write it down. So what this means is, if I again write it, c t minus lambda 1 identity, t minus lambda 2 identity, and so on, t minus lambda m identity times v. Now we read it from left to right, so we have 0 equals this guy. So what does it mean? It means v is in the kernel of this linear operator. So this means v is in the kernel of, maybe I give this operator a name, it is a bit cumbersome, of this, just, how do I call this now? Of the big operator. The big operator is the red guy I have up here, sorry. Okay, and how can it be that, so what does it mean if v is in the kernel of this big operator? It means that we can now we can now conclude that at least one of these factors as operators must be in such a way that it is not injective. I maybe write it down. At least there must exist, sorry, I write it a bit different. There must exist an I mean between 0 and 1, between 0 and m, such that t minus lambda I, the identity, is not injective. Otherwise, if all of them would be injective, then the whole mapping would be injective and then the kernel would be 0. But there is somebody in the kernel. So we know that such a guy must exist. But then it means, and now comes the where we want to head. So now it means that lambda I is an eigenvalue of t. And there we go. This is what we wanted to prove. We have now found an eigenvalue of t. Maybe let's, to really understand what's going on in this proof, it is a bit of a mysterious proof, I think, and it takes a couple of readings to understand what's going on. Let me simply repeat it once more and try to point out where the important things are. And maybe I use yellow. I can remove it later on. So we start choosing any vector. And observe, in the end, this is not necessarily going to be an eigenvector of the mapping we're currently looking at. So we fix an operator t, and we choose any vector v. Now we make this funny linear combination, the one here. Oh, sorry, this is something you can't see. How do I do this? In pink, maybe? Now we do this linear combination. We consider these vectors. We know these are n plus 1 vectors, and so they need to be linearly dependent. So what we can do now is we can find, now we're here, we can find coefficients that makes this linear combination being 0. And this all works because we have n plus 1 vectors. Now the trick is we go over to this polynomial. We interpret this vector as a polynomial, so sort of the coefficients, we take them as a polynomial. We are over C, so we can factorize the polynomial. And then we translate it back to saying, okay, the factorized polynomial also implies that we can factorize, if you want, this big linear operator. And now we know that at least one of these factors needs to be non-zero. Or if we apply this factor to this vector v that we've chosen in the beginning, then it needs to be non-zero. It needs to be so v is in the kernel, so this mapping is not injective. So we found an eigenvector, we found an eigenvalue, sorry. What is maybe a bit important to understand is this vector v, of course, is not necessarily an eigenvector of the operator t itself. And this, and the fact is also that these coefficients, these a's that we found in the beginning, where are they? Here. Sorry. Again, here the a's that we find, they of course depend on v. So we first pick v, and then we find the coefficients that makes that whole thing linearly dependent, and then we go through the whole argument with the polynomial, and in the end we just find that one of these lambda i's has to be, or that one of these factors has to be non-injective, and we found an eigenvalue, sorry. Okay. I like this proof. It's a bit of a surprising proof, but it drives it home.